Before we talk about linked lists, let's talk about arrays for a sec. So imagine we had this array that's filled with elements x, y, and z. If we wanted to add a new element, we couldn't because we've reached the maximum capacity for this array. So what would we have to do instead? We would have to initialize a brand new array, right? Let's say double the original array size to accommodate for future elements. Right, copy in all the elements, and then finally we could insert the new element b, right? But in this scenario, we have two spaces left over, and we may never actually end up using these two spaces, so potentially we're allocating space that we're never actually going to end up using. So what's the solution? The solution would be to allocate elements dynamically rather than pre-allocate a fixed size right off the bat, right? So let's say for this example, at the very start, we only add x, right? Then once we want to add a new element, we create that new element y, and then we have x point to it, right? We want to add a new element z, so we create that new element z, and then we have y point to z. Want to create a new element b, create that new element b, and then we have z point to b, right? So there is no fixed size, right? And you're creating each element as is needed, and in theory, you can have an infinite number of elements. Let's look at the formal definition of a linked list. It's a sequence of nodes that are connected, right? And each node consists of data, that's the value to be stored within the node, as well as a pointer. The pointer is pointing to the next node in the sequence, right? Let's look at an example of a linked list. So we have this first node right over here. It has data x stored, and the next node is stored at address 506. Right, so this node has data y, its next node in the sequence is at address 204. This node has data z, its next node address is at 112. Right, so this node has value b, its data is storing value b, and its next node address is null. This is the default value. This is essentially saying that there is no next node in the sequence as of yet. Something else that is useful for visualization is we like to talk about something called head. This is just pointing to the address of our first node. If we compare memory addresses in arrays versus linked lists, we see over here for the array that the array is stored contiguously in memory. Each element is taking up 4 bytes, right? So that means we can easily access each element in the memory by taking the index, multiplying it by 4 from the starting memory address. So if we wanted z, we would do 4 times 2 is 8 plus the original memory address, that's 108, so we can access z. Versus in a linked list, right, they are not contiguous, they are spread out all over the place. Each node has its own starting memory address, and the node takes up 8 bytes, 4 for the data, 4 for the pointer, right? And we can see they're all spread out. They're not necessarily in order of the sequence. There are 3 operations for a linked list. We have traverse, which you go through the linked list until the desired node is reached. Insert, add a new node to the linked list, and delete, remove the specified node from the linked list. Traversing. So imagine we want to get to the 4th node in the sequence, right? how would we do this? We are going to set a dummy variable called current, right? And current is going to initially be set to head. The reason we do this instead of just simply using head is if we were to move through the linked list using head, we would be unable to access the start of the linked list later on, because as we're shifting down, we don't have anything that's keeping track of the head anymore, right? So current is pointing to the what head is pointing to. It's pointing to address 370. So if we go to address 370, we are now pointing to the first node in the linked list. And we see that our next node address is not null. So that means there's another node within the sequence. So we can now head to the address 506. When we're at address 506, we are at the second node in the sequence. And again, we see that the next node address is not null. It's pointing to something. It's pointing to address 204. So we head to that address, and we see we are now at the third node in the sequence. And the next node address again is not null. It's pointing to something. It's pointing to address 112. So we can go to address 112. We get to address 112. We realize, okay, we have finally reached the fourth node in the sequence. We can now do whatever we want with the fourth node in the sequence. The time complexity then for the traverse operation would be big O of n, which means that in the worst case scenario, to get to a node, we have to visit every single node in the sequence, in the linked list, until we get to our desired node, right? So if we have n nodes within our linked list, we may have to traverse n nodes. To implement a traverse operation, let's first go over the implementation of just some basic things that we're going to be using. So we are going to use a node object. So if you want a node object, you need a node class, and within that you have the constructor for the class in it, and we pass in value. Value is the what's going to be used to initialize the data of the node, right? Then we have a variable called next. Next is basically our pointer, right? It's going to be how we traverse to the next node in the sequence. We have a class called linked list. This is how we traverse, insert, and delete nodes within our sequence. Our constructor simply has the head variable to keep track of the start of the sequence, right? Now we get into the traverse operation. We are going to pass in the index, which index within the sequence are we interested in, right? So if we are interested in an index that's less than 0, that's an error. There can't be, that's like an invalid input, right? If we have a situation where our head is not pointing to anything, right, that means our linked list is empty. Okay. Now we are going to initialize a variable called count. This is going to keep track of which index are we at currently. And just like our drawn out example, we have current. Current is initially going to be set to the head. Then we're going to enter a while loop, which says while we are at a node, as well as our count is less than the index that we're interested in, we are going to move on to the next node, right? And we are going to increment our count. So this breaks down in two scenarios, right? You exit this while loop in two scenarios. If you get to a situation where the current node that you're at is null, right? Or if your count is equal to or greater than index. But obviously the first scenario where this would be broken is when count is equal to index, right? So when you exit out of this while loop, you check, are you at a null node, right? If that's the case, then you've reached out of bounds. Otherwise, you are actually at the node that you're interested in which case return that node, and then you can do whatever you want with that. For inserting, you essentially have three scenarios, right? This first one is when you have either an empty linked list or you're trying to insert at the head of a linked list. So if you are trying to insert in an empty linked list, all you would need to do is create your node, right? Let's say it's data F, it's address 321, it's not pointing to anything. You would take your head, right, and you would set that to be pointing at this node. So it's going to point to address 321, and there, you've inserted into an empty linked list. Now, what would you do if you had nodes in your linked list and you're trying to insert? It's essentially the same process, right? You're going to create the node. Let's call it S. And it's going to be at address 242. You're going to set the next node address to be what's currently the head node, right? So you would look at head, you see that it's at 370, so you grab 370, you set it, and then you would update head to point at our new node. It's going to point to address 242, and now you've inserted to the head of your node. In this situation, your time complexity is going to be just big O of 1. It's a constant time complexity, right? You're always just going to be doing some simple amounts of lines depending on your implementation. The second scenario is, imagine we wanted to insert a node in between Y and Z. Well, what would we have to do? We would have to first traverse to Y. So we set current, right? It goes to head, then it goes to X, then it finally hits Y. Once we're there, we create our node. Let's say it's going to be F, and it's going to have address 345, right? We are going to look at the next address of Y, where we're currently pointing to. We see that it has address 204, right? We're going to point to, that was a horrible arrow, point to address 204, and we are going to update the address of Y to point to our new node. Our new node is at 345, right? So we've inserted in between the middle. So in this scenario, the time complexity is big O of n, because in the worst case scenario, we have to traverse through every single node in our linked list before we can insert. The final scenario is inserting at the end of the linked list, right? So let's say we had the node F, and it's not going to point to anything as of yet. The way we would insert to the end is, again, we would have to traverse. So we have current is pointing to head, go to head, go to the neck, or go to the node. It's pointing to 506, so we go to address 506. We get there, we see that there's a next node address. It says 204, so we go to 204. And then we finally get to the last one. It's null. We're at the very end. So what we're going to do is we had created this new node. Let's say its address was 563. We are going to update this next node address to be 563. It's going to point to our new address, and then we're done, right? This is one implementation. And in this situation, our time complexity would be big O of n, because in the worst case scenario, we would have to traverse through every single node within our linked list to get to the end, and then we could insert the address, right? But another scenario is, let's say instead of this was initially pointed to null, we were smart, and ahead of time we created a pointer to the tail of our linked list. So every time we added a linked list, we would update our tail. But we knew that our last node was at address 204. In this case, since we have our tail, we could instantly go to this node, update its address to the new node we created, right? 563, point it there, and then we would simply update tail, and now tail would point to 563, right? So it really depends on your implementation. Most likely your delete is going to have a big O of n time complexity, but if you keep track of your tail, the last node in your list, you could have a constant time complexity, right? Big O of 1. The implementation for insert. We have a method that passes in the value, the data that's supposed to be stored in the node, and the index within the sequence that we're interested in storing it at. So if our index is less than 0, that means obviously that's not possible. We've hit an error, so raise the exception. We're going to create our node, right? Our new node. It's going to have a data which is equal to value, and it's going to have its next pointer set to null. If we are inserting to the start of the linked list, then what we're going to do is we're going to set the next node to be equal to what head is currently pointing at, right? Then we're going to update head to be pointing at our new node. In every other scenario, we're going to follow this, right? This is if you're inserting at the middle or if you're inserting at the end. We're going to be following the big O of n time complexity for inserting, right? Whether in the middle or end. So you're going to get to the node that's right before the index that we're currently interested in, right? You're going to go there. You're going to set the next node for your, you're going to set the node after your new node to be equal to the node that the before index is currently pointing to in its next node address, right? And then you're going to finally update your before index.next to be pointing to your new node, just like we drew out in the example. For the delete operation, there's two situations to keep in mind when you're deleting the head node and any other scenario for deletion, right? So if you're deleting at the head node, what you would do is you would go look at the head node, you would see what's the next node address, and then you would update head to match that. So the next node address for the head node is 506, right? Because we see over here, it's pointing to 506. So we're going to update head to point to 506. It's now pointing here, and then for our purposes, this node, essentially, we treat it like it doesn't even exist anymore because we can't access it because head is now pointing at 506. There's no way for us to access that node anymore, right? So for our purposes, it doesn't even exist anymore. Deleting at the non-head node, we need to, let's say, delete node Z, right? What we need to do is we need to get to the node right before node Z. So we have current point to head gets us to this node. The next node address is 506. We get to the node Y, and then the next one will be Z. So we're at where we currently want to be. What we would do is we would take a peek, right, at node Z. We see the next node address for this node is null. So what we're going to do is we're going to take this node or this address and we're going to update it to be over here, right? So this node address is now null, and then we can treat this node as if it no longer exists. And this works out perfectly, even though right now this example is for a node at the end of our list, right? Let's imagine that there was a node that came after, right? And it was address 516. If we were to update this node address with this, it would still work out. So this would be address 516. It would now point to whatever node is off screen, and then this node, we don't care about it anymore, right? So it all works out. And time complexity, of course, is big O of n, because in the worst case scenario, you may have to traverse your entire linked list. The delete implementation. So imagine our method delete has a parameter called index. It's the index of the node. So which node in the sequence are we interested in deleting? If index is less than 0, you have an error, so raise the exception. If your index or if your linked list is empty, you have another error, raise an exception. If you're interested in deleting the head node, index is equal to 0, then simply update head to be equal to the next node in the sequence. Otherwise, you fall into this scenario, right? Every other scenario other than deleting the head. You want to get to the node that's right before the index that you're interested in. So traverse up to that node, index -1. Then if you get there without raising any exceptions, then what you would do is you would set the next node for that index to be equal to the index that you deleted's next node, right? So this value would be the node that we're interested in deleting. This part is the address of the node after that, right? This section right here is what causes the time complexity to be big O of n, right? In the worst case scenario, you're trying to traverse every single node. We said that this section over here is big O of 1. It's a constant time complexity. But when dealing with time complexities, you always go for the bigger time complexity within your method. So overall, the delete method is going to have a time complexity of big O of n. We can also play with a node a little bit. So we can add 4 extra bytes, let's say, for a previous node address, right? So over here we can see that we have the this side pointing to the address of the next node, and then this side pointing to the address of the previous node. So over here is pointing to 370. This allows us to traverse this way as well as reverse the way that we traverse. So we can move both directions, right? It also could potentially make deleting a node easier. For example, let's say we were at the Y node and we wanted to delete it. So what we could do is we could go to the previous node over here, right? And instead of having it point to 560, we would set it to what the next node address is for Y. So over here is 204. So the address is 204. So instead of it pointing here, we're actually pointing over there. And then we could also go to the next node over here and change what the previous node is, right? So we go to Y and we see the previous node is at 370. So we would update this to be 370, delete this, have it point to 370, and then we could essentially treat this node as if it didn't exist, right?